problem for our society these days. Okay, so hold your breath. You wanted to know how we're going to survive the coming year, how to win collective decisions. And we pointed out to me that I was a bit too strict with the Q&A, so I promise I'll be more flexible in terms of time. We don't have a too dense schedule, so you go a little bit over time. So, okay, your question, just wave your hand vigorously and you get to answer the question.
Thank you. Well, that's high expectations now, which I'm not going to stand to, but I'll do my best. Right, so this is going to be very different from what you've been hearing so far, but I had many ideas that I find useful to what I do, and hopefully and probably something from this will be useful to what you're doing, or at least, I don't know, maybe there are applications that you see your techniques apply well to, or the other way around. There are some questions or techniques that we are using that can apply to applications that you're looking at. So this is about making collective decisions. So we have a system. The system is a multi-agent system. It's composed of many components. The components have their own opinions or preferences about where the system should end up, what alternative we should choose, what decision we should make. So you can look at it as a group of individuals that have their own preferences, not necessarily given as utilities, by the way, as coming back to yesterday's talk. So I will look at a particular way which is standard in voting theory of expressing preferences, but there are also many others that people are looking at, including metric spaces and so on. Right. So we're going to look at it as a game. There are two parts here. This is pretty much a bonus. I am hoping to actually finish the first part. The first part is about voting games where the voters, the decision makers, are the strategic components. So they may strategize in reporting their preference to the collective decision-making, or in short, voting mechanism. And there's an old result from the 70s by Gibbert and Satterthwaite telling us that any reasonable, from axiomatic perspective, voting rule or a mechanism is prone to manipulation or strategic behavior. Right? We here are not going to look, we're not going to call it manipulation even. We're going to call it strategic behavior because we're not going to fight it. We're going to embrace it and see where it leads. Unlike quite a bit of research that was actually looking at complexity obstacles to manipulation. So this is a very different perspective. So the existence of equilibrium in voting settings is not an interesting question. There are plenty of these, and not all of them are good. You can think of, well, plurality voting. We will vote for our favorite candidate, or any candidate, and assume that we all somehow happen to vote for someone we all hate. It's an equilibrium, because unilaterally no one can change the outcome, right? So these equilibria are bad. These equilibria we actually are looking to eliminate with some processes. So that's also quite in spirit with what Jean-François was telling me yesterday about non-credible threats, right? Here is something different, but still we have a set of equilibria. We're only talking about pure strategy equilibria here. I'm not going to go into mix at all. So the existence is not interesting, but what's interesting is dynamics. And dynamics in the sense of, if you know potential games, congestion games, myopic improvement. So if I look at the situation right now and I see some improving move, I will apply it. Other agents will do the same. If we put no order on how things are going, will we converge to an agreement? So these are sort of questions we're going to ask here. We then will see that, well, not all dynamics, of course, will converge. So we will have to put some restrictions, and then we'll show some information or uncertainty model that will justify such restrictive heuristic dynamics as rational behavior under that picture of the world that we have, right? And then we'll look at this dynamic process, we call it iterative voting, and we'll see that they actually answer some questions about acyclic games in general. And also, these processes do help us to reduce the set of equilibria to some better outcomes. Okay. I'm going to keep it quite high level, but I'd like to tell you about these things. In candidacy games, this is just an announcement. If I get the time, I get the time. If I don't get the time, we'll talk about it in the afternoon, perhaps. But here, the candidates are strategic about their participation, in or out. In France, we have seen that pretty much so after the far right is chosen, or it is about to be chosen, then there's a candidacy games. Some candidates withdraw so that their votes go to someone better, right? So this is a candidacy game pretty much. And their equilibria are rare, in fact, but also the dynamics and reachability of those equilibria is an interesting question, and some sort of behaviors there. All right, but setting. This is a common setting for either voting or candidacy games, right? Depending on what the strategic component is. So we have agents. The agents have preferences over alternatives, right? And we will assume that this preference are given either by rankings, ordinal rankings over the candidates, or approval sets. I approve on X, I do not approve on Y. Agents report their preferences to the mechanism, and the mechanism does its magic and enforces the outcome on the whole system, on all the agents. So the natural question is, do we have a solution which is agreed by the voters, right? Or decision makers? Example: we are looking at a platform to host our project. We have Teams, Slack, and Discord, and we have, I believe, 5 voters here. Adam wants Discord, Ben and Cora Slack, David and Eve Teams. And so here we have these two in a tie. If I break the tie lexicographically or alphabetically, then what happens? Slack wins, right? Sorry, I can't hear. I do agree. I tried it once. But, well, you don't know what preferences other people have. I'm always surprised they don't think like me, but they do, right? Anyway, that's the case. But David agrees with you. Okay, David agrees with you. So Slack is his least favorite. He says, come on, just not that. And what David can do in this situation, David can move and join Adam at Discord, and now these two are in a tie, and this one wins alphabetically, right? Which makes Eve not happy because she actually hates Discord. She'd rather go to Slack, and she can enforce this decision on everyone by moving and joining Ben and Cora. Now, Ben and Cora were happy in first place, right? These guys have nothing to do now, and no one else wants to do anything, right? So that's an equilibrium. Not the one that some of us would like, but anyway. But these are sort of processes that we are looking at. Right, so this can be modeled as a normal form game, where players are voters in this case. Strategies would be their votes, their reports of their preferences, and the outcomes are determined by some voting rules. We'll talk about some common rules. Usually such a rule, when we select just a single alternative, is paired with some tie-breaking scheme, so we need to know how to break the ties, and preferences over possible outcomes of the game, the alternatives, determine the preferences of the players over the states of the game. Right? So clear. Okay. Some examples: dictatorship. Dictatorship is a voting mechanism that decides according to preferences of a particular candidate. Right? So if A is a dictator, we say A, B, C, and so on. So the raw player is a dictator here. If the raw player says A, we do A. If they say B, we do C, no matter what this one says. We have two voters, sorry, yeah. We have two voters. One votes in rows, one in columns, right? And these are the decisions. So these are their votes, their possible votes, and these are the decisions that this mechanism makes. So if we always do what the dictator says here, right? No matter. And in a similar form, this is plurality. Again, two voters, these are their votes, this is the decision. This is plurality with lexicographical, alphabetical tie-breaking, right? So if we have an AA, we have A. So basically, whenever there is agreement, this is a diagonal, and everywhere else we break it lexicographically. So C has way fewer chances than A with such tie breaking. But if we change the tie breaking, yeah.
I don't fully understand this matrix. So it's when you say A, the row is dictator, because what if row voted B?
But this is not a dictatorship anymore.
Oh,
okay. I can come back to dictatorship if you like.
I understand.
This is plurality with alphabetical tie breaking, right? So if we have two votes A and B, they're in a tie, but A wins by the tie breaking. Yeah, there's. Sure. There's no such a thing. Well, I'm not talking about political elections here. This is just one. Way. It's a pretty common way to break the ties. There are many others. There's randomized tie breaking. There's other deterministic tie breakings. There are plenty of ways. Tie breaking matters. So it's important to decide which one you employ in a particular situation, but this is all we can say, right? They do matter. This is just one of the natural ways to break the ties, and yeah, it's helpful for some results, but then we should know that if it's important for certain things, then we should not. There are other common voting rules. So plurality is part of the family which is called positional scoring rules. These scoring rules are defined by a vector of scores, the number of positions as the number of alternatives, right? And this vector actually says how many points each voter gives to each position in their ranking, roughly speaking, right? So in plurality, we would have 1 for the top position, zeros for all the rest, right? We only indicate our top choice. The rest don't get anything. We do not differentiate between them. There's veto, which is quite the opposite. We approve on everyone but the last position. So everyone gets 1s and 0 for the last position. K approval, K positions 1s, M minus, if M candidates we have, M minus K position 0s. Border is a decreasing score. So we have 0 for the last position, M minus 1 for the top position, and it's going down. Then there's buckling, which is a bit more sophisticated rule. It says, okay, for each candidate, find me a K so that for the majority of voters, this candidate is within K top positions. And then we run K approval. That's Buckley. And Copeland and Maximin, these are two rules which are so-called Condorcet consistent. So if you know the principle of Condorcet, it says that if I have an alternative that wins against every other alternative in a pairwise election, so I exclude all other candidates, I only look at A against everyone else. If A wins against everyone else, A is a Condorcet winner. Not always we have one, and not every rule would choose one, plurality wouldn't. But these two rules, Copeland and Maximin, would, and they actually are based on pairwise elections. Copeland just counts how many pairwise wins you have. Maximin also tell by how many voters actually voted for you in the pairwise election. Is there a question?
Did you have a question?
So there are more. There are plenty of voting rules. We'll look at some of these. We are looking at an iterative setting. Right? So we start with some initial profile. It's, again, natural to assume it could be truthful one, and then the voters start compromising rather than maliciously manipulating. This is pretty much our point here. Or it can be random. It really depends on the scenario. And then they change their votes in turns. For now, let's assume these turns are not predetermined in any way. Whoever has an improving move, they apply such an improving move, right? And we also do not assume any knowledge of player about preferences of other players. What we need to do to see whether I have an improving move, I pretty much need to see where the alternatives are, right? What the scores are, pretty much, if we talk about positional scoring rules, for instance, right? Knowing the scores, I already know if I can make someone else win. I don't need to know the preferences of the others. So that's what good about this setting. And we look at myopic improving dynamics of better replies or best replies. I'll talk a bit more about it in detail. No objections, we stop. Now, will we always stop? Well, the answer, as always, is it depends. What does it depend on? It depends on what the game is, what voting mechanism we're using, together with tie-breaking rule, what player types we have. Some voters may have more voting powers than the other. They may have some weights, or they're all equal, and so on. And what sort of dynamics we're using, where do we start from, what sort of moves we allow our agents to take, in which order as well, if we want to have a say about that, and so on. And positive results, some first positive results were then in plurality. We can reach equilibrium from any state. It's not every better reply would converge, but a particular type of direct best replies, I will tell exactly what that means. They would converge from any state and for any order of agents, so we reach equilibrium. And similar result, but not by us, with a star, I indicate all other people's results. Same was found for veto. And it was also shown that such iterative process actually eliminates bad quality equilibria. There were a couple of works there. So there was theoretical result by Bronze et al. About dynamic price of anarchy. They proved some bounds on how far we can be from the truthful outcome. And there were also experimental results showing that such process can give an outcome that has a higher social welfare or Condorcet consistency, Condorcet efficiency. Yeah.
Do you assume that people don't change their preferences and then you can reach?
There's no change of preferences here, no.
So
There's
as in nobody
also,
would just
but there is
randomly.
there is a change of report. So what you tell about your preferences to the mechanism. So your preferences are private to you. These are unchanged,
Okay.
right? But what you submit does. Of course, there are negative results, border key approval, and many other rules do not converge. In fact, for just two players, there is an example that there is no Nash equilibrium at all, but with three players, we already will have equilibrium, but we can use this example to create a cycle. Okay, so not many rules converge. Yes?
Finite action games, right? So how can Nash equilibrium not exist? Is it pure Nash equilibrium?
You structure Nash equilibria finite games, yes, but we look at dynamics, which we also want to be finite, right? Okay. All right, so not every rule would converge. People started thinking, all right, how about we restrict the voters and what they can do, which in fact, in some situations can be, we will show that it can be justified by how we see the world in some way if we agree with the model. Or on some electronic platforms, you can actually artificially remove certain actions. Right? So you can implement that. Second chance is a super restrictive dynamic. It says that if the current winner is not your top or second top choice, move your second top choice to the top. So clearly converges, you have up to one action to do, done, right? Best upgrade, here is your ranking, here is the current winner. Look at everyone who is ranked above the current winner, take the one with chances to win, who you prefer the most, move them to the top. Okay, pragmatist, same thing, but not with the current winner, just k-top positions. Take the one who you prefer the most, if they can win, move them to the top. However, these dynamics are, well, over-restrictive, I would say. So the question was, how restrictive should we be to actually guarantee convergence, right? And we figured two conditions. One is actually using some sort of a potential function argument. So there's some function which is based on the score. And another one is a set monotonicity, which is a recursive definition based on the sets of potential current winners who I can bring to victory if I change my vote. And if we have either this or the other type of monotonicity, these are not equivalent, we will have convergence. And we're actually looking here at the pairs, right? Voting rule and the dynamic. Will these together give convergence? Any questions so far?
So just to clarify, are the restrictive dynamics restrictions on the strategies that the players can take, or are they part of the voting rule itself from iteration to iteration?
It's a dynamic. The voting rules tells these are the votes, who is the winner, right? Restrictive dynamics is what are the allowed moves you can make. Yeah, so you actually need both. So either you allowed any better reply, best reply, and then if you have convergence, you converge to Nash equilibrium. If you have restricted dynamics, you converge to a stable state under this restriction, which is not necessarily Nash equilibrium as well, right? So, yeah, okay. Right. So what does it give us, these two conditions? Well, first of all, we could really relax previously considered restrictions. So the best upgrade, we could generalize to a dynamic where, okay, you fix the current winner, but then you can freely shuffle whatever the other candidates, as long as you move your new winner to the top, right? you upgrade the new winner, but not necessarily to the top, to any other position you consider which is sufficient, and and unit upgrade, you move them by exactly one position. So these are different dynamics, and for these we show convergence for positional scoring rules, Copeland-Maximil for the generalized best upgrade, unit upgrade for Maximin, and upgrade for Maximin and unit upgrade for what we call unit gap scoring rules. And these are the scoring rules where the gap between two consecutive positions in the score is no more than 1. So plurality, veto, K-approval, border are all like that, right? And it was the very first convergence result for Buckling at all. There were no ad hoc results before that. And later on, after we published that in a conference, we got some experiments as well, and we showed that, well, here we have a theoretical proof for unit upgrade, but experimentally we show that also generalized best upgrade and upgrade converge for Buckling. And we see that even when we don't have to end up in an equilibrium, we actually do, which is good. So, well, there are plenty of equilibria, and it's also good that somehow we can find the way to those. Now, yeah, this is the next thing that I promised to show, that in fact we can model we can model the uncertainty that we have about the state of the world. Let's say we have a voting poll, right? It's not certain that this is how people will actually vote. So there is some uncertainty about that. You may have some uncertainty about what other people actually prefer, what you actually prefer in certain situation, and so on. And there are two natural ways to model uncertainty. One is with probabilities, give every state of the world a probability. Another one, that's another extreme, it's strict uncertainty, when you consider events either as possible or impossible. Right? I haven't talked about this slide yet.
You have a vote.
Yeah.
Now, before it was individuals made a decision to change their vote, right? What is this heuristic now?Ho is changing? I don't understand.
I haven't talked about it yet. I'm going to.
Okay.
Yeah. So heuristics, the moves that you can make is a function, right? Is a function of the current state of the world, of your preferences. So given that, you have a function, a heuristic function, that decides what will be your next step. Are you going to change your vote? And so this is what this function decides. And every restriction of what votes are available to you can be modeled as such a function, right? So this is actually, our dynamics can be modeled by a function that takes the state of the world and computes the next step. Now, what we are trying to build with this, we are trying to build some epistemic model of the world with some, which is not the probabilistic one, but not strict uncertainty one, something in between, where the particular restrictive dynamics that we looked at, when modeled as such a function in this framework, will be justified, will be seen as rational decisions in this model of uncertainty. Let me move to.
I'm still not sure I understand the difference between dynamic and heuristic. What's the difference?
Heuristic is a function that you employ at every step of the dynamic. This is the state of the world.
But you had before different dynamics. They were all heuristics in some sense, right?
Each one of them you can write
heuristic.
as a function, right?
Yeah.
So better reply every other vote is possible.
So now you're just generalizing.
Now I'm formalizing
Okay,
it,
okay.
yeah, and building on top of it, and building with it some framework, exactly, yeah, to also talk about things I already have. So yeah, we can define such a function, and we can formalize our dynamics with it. There are also some other functions that we can employ. Some voters prefer to tell truth whenever they're not pivotal. They just switch to telling the truth rather than their previous vote, whatever it was. Or they're lazy, they would abstain if they're not pivotal. Leader rule is a rule if we have the alternatives ranked with their current scores, right? And this is an approval rule. And as a next step, you would approve on everyone who is beyond the current winner in your ranking, and you will only approve the current winner if you prefer them over the runner-up. So you only approve the current winner or the runner-up, only one of them. Okay, that's the rule. Local dominance, this is a strict uncertainty model that divides the states as possible and possible. So I have a poll, these are the scores, and I assume that there is some radius at which the states are possible, right? So my vision is just a bit blurred on what the scores are, right? So I give it some radius. And all the states within this radius I consider as probable. So my next move I will consider against these ones, right? So that's local dominance. Not last, super simple, if I'm currently not voting for the last alternative, I'll vote for someone else randomly. Just not the worst one. Just not the worst one. The information structure that we want to propose is, as I said, something in between probabilistic and strict uncertainty. So this is some hierarchy of likelihoods of how probable we see certain events, right? So there is, and there's some structure where the next level includes the previous one. So the states which are close to the current state are more likely, right? But they're less certain. And the more kind of freedom we get to that, so now I can consider this profile is also certain, which brings these two candidates to the tie, and all these consecutive levels and the farther states from the original state, they're less likely but more certain. So eventually some of them will happen. Right? Well, you can apply different sort of metrics, and for different metrics you would have different results, clearly. But the idea is to just see it in this way. What we do with this, I'll tell that in a moment. So for voting decisions, what's important is what you see as a tie here, where you're pivotal, because only then you will make a move. And this is what matters for us. So the idea is common in game theory and also used in the local dominance notion that I mentioned before, that agents will not take dominated actions, right? What we would consider is dominated. So we define ordinal dominance here because we have ordinal preferences in this levels of uncertainty, and we say that a particular action ordinally dominates B, ordinally dominates another action B prime, if it's better for our agent in some level of uncertainty, in one of these rings, right? And undominated would be one that is not dominated in any of them. And these are the actions that we are going to take if we have a move. So, right, we are not playing dominated strategies. Now, when we pivotal in the voting settings, this is when we have the winning candidates in a tie. Only then we are going to take a move. Otherwise, we don't change the situation, right? And to every information structure, we can associate it with a graph structure, what we call pivot graph, and this graph actually indicates whom do we see in a tie, right? So the winning candidates are more likely to tie but less certain, and then the other ties appear as more certain but less likely, right? For example, in our original state, we didn't have any tie at all. Then with a little bit of uncertainty, these two candidates seem as in a tie, even if maybe it's not precisely so. Then we see more agents in a tie, and eventually everyone can be in a tie. And we say the following. We say that, okay, if we take this epistemic model of the world, in this model, and if we take the idea of ordinal dominance, that we do not play dominated strategies, then we would say that a particular pivot graph structure would justify a heuristic if indeed all the actions that this heuristic tells us to play would be undominated in our pivot graph. And if we say that, okay, there's nothing to do, that means that the current action is undominated. Yeah. And we show that some of the heuristic that we looked at can be justified by certain graph structures. So the not last heuristic, when you just don't want to vote for the loser, is justified by a complete graph because you would go for anyone else. It's pretty easy to see. A star of top k candidates justifies the k-pragmatist. The local dominance, it would be a graph that is induced by some radius around the current state, and some variations of that also work for truth and lazy bias. And for the leader rule, we have this inner and outer graph where we have, so this is the current winner and the top runner, and these are all the other candidates. So that's the leader rule. And what it also gives us is the convergence result for plurality and veto under this epistemic model of uncertainty. So if we have a graph so if we have agents whose models are cliques, even though these cliques don't have to be the same, so they don't need to see the world in exactly the same way, but they need to see it as cliques, then we have convergence for plurality. Right, so I don't know what time is it. I still have time, but yeah, that's the exit point number one, which we're not going to take. But what we've seen so far, yeah, we don't need dictatorship. We can actually embrace strategic behavior. It's not necessarily bad. It actually gives us some agreed and good decisions. And iterative voting is a way to do that without much work, in fact. You just let people to converge, right? In some way. Maybe you restrict them in some way, but right. And the next thing that I promised to show is that actually voting games, even though, okay, we define them in a particular scenario, which the definition depends on, of course, but with these games, we we were able to disprove a couple of conjectures about acyclic games in general. I'll show you how. So let me just tell a bit more about different degrees of acyclicity. So I assume people are familiar with congestion and potential games, more or less. Congestion games, potential games. Okay, I'll tell what we need to know. So we talked about myopic dynamics. I see the current state. I apply a move. I improve my utility or my outcome, right? So the most free and strong acyclicity property here is any improving move path would converge clearly to Nash equilibrium in such state. Right? This is called finite improvement property. Similarly, finite best response property is when not any improvement, but the best possible improvement that you're taking. Finite direct response only makes sense in the case of voting. You directly vote for the candidate you bring to victory. So you directly choose the alternative that will win. And direct and best together, right? And these three are different levels of what sort of freedom, not in the moves themselves, but the order in which you apply them. So strong acyclicity for any selection, for any order of players, no say about that at all. And any replies, either of this or this sort, we have convergence. Order free, we say nothing about the order of players, but we restrict their moves somehow. And weak, we restrict both. So weak acyclicity will say, okay, not every path will converge. We may have cycle, but you can find one, right? Order free would say, well, you only can tell them what not to do, but then they're free to go in every order. And here, whatever goes, right? Very simple example with two agents shows a cycle. No way. Yeah, that'll be. If that's the, perhaps you can do something with groups and more, but yeah. Right, and so if we have finite improvement property, of course we have best reply and direct reply conversion. All of that implies direct better replies, and these are, if we have order-free property, we have weak notion of it, and then, yeah, if it's for some replies, then of course that's for better replies. Now, there is, so I already mentioned this notion, the potential function notion. It comes from physics, so intuitively people understand, even if they don't know this particular literature, but it's a function. So that's the result by Mondor and Shapley from the 90s, from 96 specifically. It's a function on the strategy profiles with the property that, well, there are different degrees, but the property is what's important, that the function changes along the strategy profiles, but it's changing with a unilateral deviation of a specific agent, which is not the same agent along the path, right? And if we have such a function, and we are talking about finite number of states, right? If we have such a function that monotonically changes along the improvement path, we end up in a local optimum, right? So that gives us a stable state. Equilibrium or stable under certain restrictions doesn't matter. And there are different degrees. So exact potential, the function actually, the increment in the function is exactly the increment in the utility of a player. For that, we need cardinal utilities. So such a function defines a class of what we call potential games or congestion games. These are equivalent. A weaker notion, it increases if and only if the utility of a player increases, but not necessarily by the same amount. And there's a theorem telling us that in the voting context, a game would have an ordinal potential if and only if it's a dictatorship. So that's a lot to ask. But there is even weaker notion of potential, which is generalized. It increases every time when there is a better reply, but it may also increase when there are other steps, right? So whenever an agent makes an improving move, also the function grows, but it also can grow in other places. And that already is sufficient for the finite improvement property, right? That's easy to see. So we end up at a local optimal there. So what we didn't know actually is what games, we didn't know. There was a conjecture that every game that has this generalized ordinal potential, the finite improvement property, has to be of a certain form. It has to be separable. What does separable mean? Is it means that every voter has some function that maps his vote to a particular alternative. Plurality is like that, dictatorship is like that, lexicographic rule is like that. And the outcome is taken from these votes, right? So for instance, in plurality, these functions are my top choice, right? And then one of these top choices will be the outcome of the whole election, right? If the rule is like that, it's a separable rule. The conjecture was that if you want a game, if you want a finite improvement property, every better reply path will converge. You need a separable voting rule. What we showed, you don't have to. So the construction is, it's not too complicated actually, but we needed enough agents to build it. And this is a voting rule which gives us a non-separable game that has an FAP. The idea there is if you have binary choices for the voters, then for a separable game, we only can have 2n possible outcomes, right? However, there are 2 in a power of n voting profiles. And then what we can do, we can define a game rule that would have 2n plus 1 possible outcomes. This is some z where all the 2 in the power of n minus 2n profiles go to. So they will give us the same outcome. And then you can somehow put these in a space so that there is a path through this same outcome between every distinctive original outcomes, right? And this is not an improvement path then. So that was one thing. Another remark from the same paper by Kukushkin, which I didn't say, by the way, was that we don't know a game that would be weak acyclic but not order-free acyclic. And indeed, for instance, plurality with lexicographic tiebreaking is both weak and order-free acyclic. Well, we have that, we clearly have that. What we show is that if we have randomized tiebreaking already with plurality, then while we have weak acyclicity, here we break the order-free acyclicity. So we need to tell the agents in which order to apply their moves. And the example of that, I'm not going to into details, yeah, but this is just 4 candidates and 3 voters, and there is a cycle here, so you may end up in a cycle, but from every state, there is a path that would give us some stable outcome, right? So you just can't take every path. You need to know where to go, and you will end up in a stable outcome. Right, so that's another exit point, which I believe we are going to take. And it tells us that voting games do help to get knowledge about acyclic games in general, right? So we now have an example of a strongly acyclic game, which is non-separable. And we also have a first separation between weak and order-free acyclicity, telling us, okay, indeed, it's not the same thing. And these are some tables with convergence results, but I don't think you have much interest in that. So any best replies do not quite converge, but more restrictions we give, the better the world is. And this is for other rules. Of course, the picture is less pretty here, but there is still some hope for something anyway. And I'll stop at that before we move to, yeah.
Talk about convergence, but you didn't talk about how long does it take to converge.
It's polynomial time whenever it converges. The problem is that in most cases it just doesn't.
What kind of polynomial?
Quadratic in the number of voters and the number of candidates.
Okay, so even that tells you this is okay if you have maybe 5 friends trying to decide where to go for dinner.
Right,
But
well,
when I have, let's say, 20 faculty members trying to decide whom to hire, and you tell them, oh, well, okay, just in 400 rounds we can converge, it's not going to, not going to go very well.
This sort of criticism should be not about the time of the time of convergence, actually, but you're not pivotal if you're too many.
Hmm?
You will not be pivotal. You will not have an improving move if you're millions, right? As an individual. So all these discussion makes sense in elections which are small enough for an individual to be pivotal, or you can think, okay, this is actually a group of individuals who have similar preferences, and they move.
So the title should be not how to make collective decision, but how to decide which restaurant to go to for dinner.
Well, I think is what.
I was hoping we can take your talk and change the next election, but I don't think it's going to work.
Well, if we go for political elections, we need to change the voting system, and there's quite a bit of knowledge about what voting systems would do better than what we have.
Yes.
Right.
Work the same way or change the same way.
Say it again.
So if you have 100 people, but they're really 3 people replicated some number of times, so they always act exactly the same way. That reflects the societal fabric better. Then would you converge still quadratically on 100 or quadratically on 3?
The active agents, if whoever doesn't do anything, does not take any steps in the dynamic, right? So of course, worst case, so if you know that some agents always vote the same, you only take them into consideration to compute the outcome, but in the dynamics they do not participate. So only those who are active, of course.
No, but they're all active, but exactly the same way. They do exactly the same.
You can see them as one player with a particular weight, right?
So then you will converge faster.
Yes. What I was trying to say is one agent in a million of agents is just not pivotal. So it's a deeper criticism than the rate of convergence. It does apply to small elections where a voter can be a group of voters who coordinate their actions and so on.
Other questions, comments?
So maybe this is more appropriate for the panel discussion, but I really like the fact that there exists a negotiation. And what Jean-François talked about was very much about choosing the best, and arriving at an equilibrium. And we didn't discuss so much the results about the price of anarchy, like how far is an equilibrium that you get to from some kind of optimal. And in a way, taking this to my kind of games and applications, we don't have a way of negotiating, and we don't have a way of arriving at decisions together. And one of the previous talks highlighted the usage of synthesis for autonomous cars, and they said, well, in order to join a lane that is already active, you need some kind of negotiation. So I think this is, as a comment, this is very interesting. Thank you.
Well, you can see it as some silent way of negotiation, right? I change my vote. This is what I tell you about my.
But for example, are they allowed to communicate with each other between changing votes?
The whole point is that they don't need to converge to something good.
But suppose they could negotiate.
Well, then it's not
change?
voting anymore, right? Then it's not voting anymore. Then you already talk about changing preferences. It's a different setting.
No, let's put, they're not changing. I just what are you going to do? What are you going to do? Okay. I didn't quite understand also, how much do they know about the votes? Do they know just the winner? Do they know everybody's preference? Do they know everybody's vote? It was not clear to me.
I did say that. They need to see the scores. They need to see who is winning with what score. Then you will know if you can do something about it.
But they don't see the individual votes.
They don't have to.
They don't have to.
They don't need.
What if they do?
Well, it will not change anything here. They can run this whole thing in their mind. That's all. So you can see it as just an algorithm, not an actual dynamic that actually takes place, right? It's just an algorithm which is not very prescriptive, if you like.
But in a way, I do see it as a communication, right? So every round you reveal some information, you change your vote, and it's a limited form of communication, but you communicate something to.
Of course.
Yeah, because it's a one player, only one player all the time. So yes.
Thanks. More of a technical question. I'm just curious about whether the number of pairwise preferences available at every round would affect anything about like the rate of convergence. Would that just maybe affect like the number of rounds that would be involved?
What do you mean by pairwise preference?
I was referring back to the example you gave of like the original choice between whether they're going to meet on Slack or Teams or Discord. Like if there were like an arbitrarily larger number of options available that they're choosing from, would that just change the number of rounds or the length of time, or how does that factor in to the results?
I'm not sure I entirely understand the question. So it's pretty much what Michelle was saying. If we know the preferences, right? Then if you know the preferences, you can compute all equilibria. Which one you will end up with, that's the whole point here. There are plenty, and there are bad ones. So you know the preferences, or you can say, okay, I would assume that initially people will vote truthfully. Then, okay, are they happy with that? Probably not. What's the closest in some way stable solution? But then again, the only difference, you apply that in your mind with knowing preferences.
So it would ask more of people, I guess, in that sense. If there's more options, you'd have to have complete information of each person's like ranking, or even they would. I guess.
Yeah, but you would converge to one without complete information. That's the whole point. Okay.
change your questions until we converge.
Yeah. But we only have quadratic time for that.
But once, twice. Okay, let's see.
Sold. Thank you.